So earlier in the module, when we were looking at a single random variable, we wanted to know how much values of that random variable tend to vary. We looked at the variance, which kind of measures the spread of typical outcomes of a random variable. But now we've got two random variables hanging around. So we might want to know how they vary together. And so to find out how two random variables vary together, we look at the covariance, which is like variance, but for two random variables. So as a reminder, we had that the variance of a single random variable was the expected value of x minus its mean, all squared. Its expectation, sorry, all squared. I'm calling the expectation there mu x, just because we might have multiple random variables hanging around. So the covariance of x and y, and this is the definition I'm writing up here, is it's the expectation of x minus mu x, but instead of squaring it, we then put in the same thing for y, so y minus mu y. And mu x and mu y are the expectations of x and y, respectively. So this is the formula for covariance. Before we use that properly, I'm going to tell you something that ought to be extremely unsurprising, which is that given we have this definitional formula for covariance, should be totally unsurprising that we also have a computational formula for the covariance. You might even be able to guess what it is. It's expectation of xy minus mu x mu y. I'm not going to prove that here in the video. I reckon you can probably prove it yourself, given that you've already seen this done many times. But there's proof in the notes if you need to check. So that's the computational formula, which tends to be more useful if you're actually trying to calculate this in real life. So let's do an example of calculating a covariance. So you'll remember that in previous subsections, we were looking at this coin tossing example where x is the number of heads in the first two coin tosses and y is the number of heads in the first three coin tosses. So let us note that marginally x is binomial 2.5, so we know that mu x is 2 times 1/2 equals 1, because the expectation of a binomial np is n times p. Similarly, we know that marginally y is binomial 3.5, so mu y is 1.5, or 3/2, marginally. So we're going to use the computational formula to find out this covariance. So what we need to find is the expectation of x and y. So given what we said in the last subsection about expectations of functions, we know that this is the sum over x and y of xy times the probability mass function pxy. So basically we have to go through like all 6 entries in that table of the joint distribution we had back in the previous subsection and add them all up. So you might remember that the first section was the x equals 0, y equals 0, x equals 0, y equals 0, and that had probability pxy 0, 0. And then we had the x equals 0, y equals 1, pxy 0, 1, and so on through all the sections of the table. It wasn't 6 entries of the table, was it? It was 4 times 3, 12 sections of the table. So I'm not going to write down all 12, but the last one would have been the x equals 2, y equals 3 cell of the table. Pxy 2, 3. And if you go back and, well, 0 times 0 there is 0. Probability of 0, 0, if you go back and look at the table, was an 1/8. Similarly, 0 times 1 is 0. That probability was also an 1/8. If we keep going up, the probability of a 2 and a 3, which makes 6, that was also an 8. It wasn't the case that all the things in the table were an 8. Some of them were 0 as well. But it just so happens that the 3 I wrote down here are all an 8. And so if you do calculate all 12 terms, the answer comes out as 2 there. You're welcome to go and check that yourself. If you want, I didn't want to write out all 12 terms here. So the covariance of x and y from the computational formula is expected value xy minus mu x mu y. We've just worked out that the expected value of xy is 2. Mu x and mu y are up there. They're 1 and 3/2. 1 times 3/2. So that comes out, I think, as a half. So the covariance between those random variables x and y is a half. So one very important thing about the covariance is that it does interact with the idea of independence in an important way, which is this. If x and y are independent, then their covariance is 0. You do have to be a little bit careful about the direction of implication here, right? It's if independent, then covariance equals 0. You should be careful not to accidentally turn that statement the other way around. We can, of course, use what's so-called the contrapositive, which means if P implies Q, then not Q implies not P. So it's also true that if the covariance is non-zero, then x and y are not independent. That's true. But again, I want to be careful to avoid swapping around the order of implication in that. Note, in the case that we just did, we found that the covariance was a half, which means it's non-zero, which means that our x and y are not independent. We already knew that. We checked the definition earlier. But this gives a second proof that our x and y are not independent. Again, there's a proof of this statement in the notes, which I would recommend you read, but no, in fact, let's do it here. It's only a one-liner, isn't it? Proof. Remember that we said in the previous subsection that if x and y are independent, then the expected value of xy is the expected value of x times the expected value of y. That was a theorem in subsection 7.4. So if that's true, then using the computational formula, we have the covariance of xy is expected value of xy minus mu x mu y, but the expected value of xy is mu x mu y, so we've got mu x mu y minus mu x mu y, and that of course is 0. So that's why it's the case that if x and y are independent, then the covariance is 0. More properties of the covariance. A lot of these are kind of similar to things we already know about the variance. One that's kind of immediate straight from the definition is that covariance of xy and covariance of yx are actually the same. Right? It's obvious from the definition that if you swap the order of x and y, you get the same definition. It might take you a fraction of a second just to check, but if you put x into the covariance twice, just think about that for a moment, you should be able to convince yourself that that comes out as the definition of just the variance of x. So if you put, it's kind of a silly thing to do, but if you ever end up with a covariance xx in some formula, that's just a variance. If you have a constant in just one side of the covariance, then you can bring it outside. Obviously, if you have a constant in both sides, that's different. But if you've just got an a in one side of the covariance, you can bring it outside. If you shift one of the variables up by b, that doesn't make any difference to the covariance in the same way that shifting didn't make any difference to the variance. And if you've got a kind of linearity in one of the terms, then that's fine. You can split it up. That's covariance xy, covariance xz, sorry, plus covariance y. So covariance is all very nicely behaved. In fact, in some ways it's nicer than the variance, because the variance you have to worry about squaring constants when they came outside, but here you don't. So what's going on here? The first one and the second one, I think, are so easy that we don't need to say anything. You just need to check the definition. 3 and 4 are on the problem sheet. So that one and that one are on the problem sheet. And number 5 is in the notes, but it's only a couple of lines. So I won't bother doing any of those live to video. But the first 2 are very easy. 3rd and 4th ones you can see in the notes, and your tutor will explain it to you at your tutorial if you get stuck. And the 5th one is in the notes. I recommend reading the one in the notes before trying the ones on the problem sheet, of course. Incidentally, I could just mention as a sort of passing comment that these ideas we have here do actually give us a different way of calculating the covariance in our coin toss sense. Because remember, y was the result of the first 3 coin tosses, and x was the result of the first 2. So we could write y equals x plus z, where z is the 3rd coin toss. So Bernoulli a half. Right, because x is representing how many heads in the first 2, z is representing how many in the 3rd, and then y is all 3 of them together, so the 2 in the x and the 1 in the z. So we could write it that way, where x and z are, of course, independent, because they're separate coin tosses. If we did it that way and wanted the covariance of x and y, we would notice that that's the covariance of x and x plus z. Then we'd use the rules about what happens if you add things inside a covariance to make that covariance xx plus covariance xz. This term is, well, covariance xx is a variance of x. This term, x and z are independent, right? So that's going to come out as 0. X and z are independent, so their covariance is 0. Variance of x, for those of you who remember, that's n times p times 1 minus p. Right, so here that's 2 times a half times 1 minus a half. That's just me remembering what the variance of a binomial random variable is. So that comes out as a half. I think if I scroll up, it's going to be what we found it was earlier. Yes, there it is. So that's another way of showing that the covariance is a half. I don't know which method you find simpler, but there you go. Okay, so now I want to go back to talking about just the normal variance, but the variance of a sum. Right. So we looked at the expectation of a sum and we had this nice linearity result. So what happens if we take a variance of a sum? Variance of x plus y. Well, the answer is you get a variance of x and you get a variance of y, but you also get a crossover term. And the crossover term is twice the covariance. You can think of this as it's a bit like multiplying out of brackets, right? If you have x plus y squared, you get an x squared, you get a y squared, but you get a 2xy as well as the crossover term. And that's a bit like what we've got here. If you've got a variance of x plus y, you've got a variance of x, you've got a variance of y, and you've got twice a crossover term. But of course, if x and y are independent, then this covariance term is 0, right? We said that a moment ago, that if x and y are independent, then the covariance is 0. So if x and y are independent, then we do have a nice, pleasant variance of x plus y equals variance of x plus variance of y. Again, important not to get the direction of implication wrong there. It's if x and y are independent, then the variance of the sum is the sum over variance, and you don't have to worry about the awkward cross term, the 2 cov. So remember, the expectation of a sum is a sum of an expectation always. A variance of a sum is a sum of a variance if they're independent. It's easy to get those mixed up in your head and end up getting them like crossed over or getting them both. The expectation of a sum is a sum of a variance always. Variance of a sum is a sum of a variance if they're independent. So again, for this theorem, there's a proof in the notes. It's just a few lines. There is one last thing I finally want to talk about in this section on the covariance. You might remember that way back in section 1 for data, we talked about that whilst you can calculate the sample covariance for some data, it's actually often more convenient to normalize it and look at a correlation instead, which tells you whether or not big values of one variable are associated with big values of the other. And so similarly, it's sometimes useful to do the same with random variables. Maybe not quite often as useful, but we do have a concept of correlation for random variables. So let's define that as the last thing in this section. So the definition here is the correlation of random variables is we take the covariance, but we normalize it by dividing through by the 2 standard deviations, that is the square root of the variances. And just like with the correlation we had in section 1, this is a number between -1 and 1. If it's close to +1, we're saying high values of x associated with high values of y. If it's close to -1, we're saying low values of x correspond to high values of y, and vice versa. If it's near 0, we're saying like x and y don't have much effect on each other. And in particular, if x and y are independent, then the covariance on the top is 0, so the whole thing is 0. So if x and y are independent, then the correlation is exactly 0. If the correlation is near 0, we're talking about kind of like not much effect. So that's a correlation for random variables. Just to look at our coin tossing example again. So correlation of x and y for those. So we found the covariance earlier in 2 different ways, and we saw that it was a half. We know that the variances, we worked those out earlier, are 1 and no, wait, where did we calculate the variances? Oh, we didn't calculate the variances. We calculated the means. So let us note that the variances are NPQ. So here, that's a half. Here, sorry, NP 1 minus P. So here, 3 times a half is 3/4. So those variances are half and 3/4. So if we come back down here, it's the square root on the bottom of half times 3/4. What have we got? We've got 8 for square root. I believe that comes out as square root 2/3 equals 0.816. Yeah, that looks about right to me. So there's quite a high positive correlation between those two, which means that if you get lots of heads in the first 2 coin tosses, it's quite likely you'll get lots of heads in the first 3 coin tosses, which I think is unsurprising information, but it's useful to be able to calculate the correlation of those things. So that's quite a lot of things that we've said about covariance, correlation, and variances of sums.